among the most exciting structures in the universe, but their actual existence has not yet been proven. In numerous science fiction movies, these cosmic objects are used to travel back and forth between two distant points in space within a few moments. But what is the theoretical basis for these breathtaking structures? How likely is it that wormholes actually exist? And if they do exist, could we one day really use them as galactic travel tunnels? In today's video, we're looking for answers. Want to join us on our journey to the greatest mysteries of the universe? Wormholes. In fictional works like Interstellar or Stargate, when the goal is to get to a distant region in the universe as quickly as possible, traveling through a wormhole is always the most promising alternative. But trips into the past can also be mastered effortlessly with the help of cosmic structures. Wormholes in the science fiction world can be thought of as galactic shortcuts or windows into the past. But what does science have to say about these exciting variations of representation that we can marvel at again and again on the big screen? In order to understand the theoretical background of the possible existence of wormholes, we first have to take a short detour to Albert Einstein's field equations of the general theory of relativity. Basically, the postulated structure of space-time denotes the common representation of three-dimensional space as well as one-dimensional time in a coherent, four-dimensional mathematical structure. All forms of mass, energy, light, or electric charges have a direct influence on the geometrical properties of space-time. Space-time itself also exerts an influence on all objects in it. Specifically, this galactic effect is gravitation. Basically, experts speak here of a curvature of space-time. To approach the gravitational field of a specific energy distribution from a mathematical point of view, the so-called Schwarzschild solution is the simplest variant. This is a solution which describes the gravitational field of a homogeneous, not charged, and not rotating sphere, while the Schwarzschild metric can even describe the gravitational field of the Earth in good approximation. Its possibilities are exhausted when it comes to describe a black hole. By means of the Schwarzschild metric, one obtains with respect to a not charged and not rotating black hole three different space-time geometries as solutions. Besides black holes, there are also white holes and wormholes. While black holes have always been known to irretrievably absorb all matter, radiation, and other information passing their event horizons, white holes are the exact galactic opposite. These hypothetical entities continuously eject mass, while at the same time, it's impossible to cross their event horizon from the outside to the inside, since black holes have, in addition to their outer and inner spaces, corresponding mirrored spaces. A theoretical transition to a white hole ultimately results. The connection between these two galactic gravitational anomalies is called the Einstein-Rosen bridge, while the whole connected structure with all its components is called a wormhole. In principle, it's conceivable that wormholes connect two places of the same space-time, or even points of different space-time of a multiverse. So far, however, there is not a shred of experimental evidence for wormholes in the scientific community. In fact, many more detailed investigations brought the realization that wormholes must be immensely unstable. Thus, Stephen Hawking suspected that normal matter particles falling into a wormhole could quickly lead to a complete collapse of the structure. In order to secure the wormhole connection, a special galactic stabilizer would be needed: exotic matter. Exotic matter. The general designation, exotic matter, is extremely broad within particle physics. Basically, it refers to particles that are not composed of protons, electrons, or neutrons. Often, the term refers to an unverified form of matter that has a negative energy density. The problem is that the existence of such matter has not yet been proven. Applied to the example of wormholes, within which exotic matter represents a stabilizing factor, it would have to exhibit anti-gravitational properties in addition to its negative energy density. However, how such a form of matter might be produced, or even how wormholes would be created with it, is still a gigantic mystery, the solution to which is currently not in sight. The assumptions of experts say that a wormhole with a diameter of just 1 meter would need exotic matter of the mass of Jupiter. The researcher Matt Visser, on the other hand, put forward the thesis that wormholes could possibly be created with tiny amounts of exotic matter. The scientists from Victoria University in Wellington also speculated that special forms of cosmic strings could have formed wormholes even in the earliest phase of the universe. In purely theoretical terms, the stunning objects would thus be detectable with the help of the gravitational lensing effect. Although we cannot say with absolute certainty whether wormholes exist at all, there is one central question. Supposing that the galactic connection tunnels really existed, would it then be possible for us to travel through them? Travel through a wormhole. In short, we don't know for sure. In order to approach the question of whether travel through a wormhole would be possible, its basic characteristics would first have to be researched. Will a future technology ever be able to create wormholes artificially? Or are they fixed components of the universe that cannot be manipulated or created by human hands? Will they remain permeable forever? Or will they only be passable within a limited period of time? Furthermore, we know nothing about what process might underlie the formation of wormholes. As we can see, the hypothetical journey through a wormhole is still subject to countless unsolved mysteries. However, if it were possible to fly through a wormhole, we might have found a galactic way to travel through time. While it would be possible, at least in theory, to get to a point in the future due to time dilation, we could possibly master a journey in the opposite direction of time with the help of a wormhole. This would require one end of the object to be accelerated to relativistic speeds. Because of the missing exotic matter, quite a few experts assume that the journey through a wormhole, if one could be found, would end in a great catastrophe for the participants. Due to the high instability, which is attributed to wormholes, even the smallest disturbances, as for example the entrance of a spaceship, could lead to the collapse of the entire structure. Within this process, the white hole would ultimately separate from the black hole. Scientists agree that white holes alone, however, are not viable. Consequently, it would therefore dissolve. What would remain would be a spaceship caught in the black hole, which would never again be able to overcome its event horizon from the inside to the outside. The acting tidal forces of the singularity prevailing there would split the spaceship within a blink of an eye into its atoms and pulverize it completely. Isn't it therefore impossible in principle to pass through a wormhole? Provided that we are not able to raise the necessary mass of exotic matter? If one follows the explanations that experts Aaron Wall, Daniel Jaffaris, and Ping Gao introduced in the field a few years ago, the hope for the use of these galactic travel tunnels is not yet lost. The theoretical physicists found within their research new types of wormholes that can be traversed in principle. The groundbreaking fact was that the corresponding wormholes do not require exotic matter with negative energy density. The required anti-gravitational negative energy could be generated at the mouths of the wormhole from the outside, namely, from special quantum connections. As soon as an object falls into the existing connection of two black holes, it could, by the effect of certain events in the outer universe, eventually emerge again from the second black hole. This scenario described by Wall, Gao, and Jafferis is, from a purely mathematical point of view, the equivalent of quantum teleportation. The discovery of these novel wormholes was based on the so-called ER-EPR conjecture of the Argentine string theorist Juan Maldacena. This assumes that wormholes between distant places of space-time are equivalent to entangled particles. This thesis is thereby also consistent with the view that space itself is also formed by quantum entanglements. Possibly, wormholes take a central role in the stabilization of space-time, allowing information to cross the event horizon of black holes from the inside to the outside. The information, which apparently disappears in the first black hole, would reappear in reality in the second black hole. The two structures would be casually connected with each other by the wormhole. The two black holes are again quantum entangled. Since it concerns a form of quantum teleportation, use of the traversable wormholes as cosmic time machines would be unthinkable, however, because the transmission of information here cannot happen faster than the speed of light. However, only transmissions with superluminal velocities could be used for time travel. If this scenario described by Wall, Gao, and Jafferis should correspond to the truth, it would also decode the information paradox. Then subscribe to our channel and activate the bell to never miss one of our videos in the future. With a thumbs up, you show us that we can keep you engaged with the content of our posts.